the chest wall off, you don't really see the heart, do you? That's what you see. And you see the thing that you see mostly is lungs. And the problem with lungs is, as you know, ultrasound, which is a high frequency sound wave, doesn't pass through air where the molecules are spaced out well, so you can't take an image. Which means if you're going to see the heart with ultrasound, you can't shine it through the lungs. You have to shine around the lungs, which means looking here, or here, or here, or here, where there are small points where there's no lung between the probe and the heart. So where's the heart then? And you should just know these words. The heart's in the middle mediastinum. If you think where is it on a side-to-side basis, then actually pretty much it's in the midline, isn't it? It's slightly to the left of the midline, but essentially a midline structure. So 2/3 of the heart in the left hemithorax, 1/3 in the right hemithorax. You should be aware of the major things that are around the heart. So it sits in the diaphragm, doesn't it? The thing you can see in front of the heart is the thymus. You see that in young kids. You don't see it so much in adults, or you don't see it in adults, but you see it in young kids. That's where it is. You see the great vessels, superior vena cava, inferior vena cava, which join to make the right atrium, which sits towards the back. In front of that is the left ventricle, which is what you see, is the right, sorry, which sits towards the front. In front of the right-hand side of the screen, you can see the right ventricle. Behind that, you see the left atrium and left ventricle. You can see the great vessels which leave the heart, the aorta which comes out, loops round and comes down, and the pulmonary artery which comes out close to the aorta, slightly anterior to the aorta, at an angle like that, and splits into right and left pulmonary arteries. The things that you need to be able to particularly identify from this are SVC, main pulmonary artery, right and left pulmonary arteries, and the head and neck vessels. And if you look at the head and neck vessels, you can see there's 3 of them, not 4. And as you come out the aorta and go round, the first one you come to is a big vessel, which then splits into 2. And it splits into the right subclavian and right common carotid. The second vessel that comes off the aorta and the third vessel are the same for the other side. That's the left common carotid and the left subclavian, but they come off individually. They don't come off from a common trunk. So there's a difference between what happens in the right arm and the left arm in terms of the origin of its arterial supply. You need to appreciate that and understand that. I'll come back to that. If you take the lungs away, you still don't see the heart. What you see is the bag the heart's in, which is the pericardium, which is a dual layered structure. It's welded onto the diaphragm down at the bottom, as you can see. And we'll talk a bit later this afternoon in detail about the pericardium, but essentially it's a 2-layered structure with a gap in the middle. It's got a small amount of fluid in it, and that fluid acts like an oil. And the job of the pericardium is to protect the heart, is to put it in some place where it can move without friction. Okay, I've already said about the position of the heart, 2/3 left hemithorax. Here you can see quite nicely that the great vessels cross over at right angles, the pulmonary artery and the aorta, and that's a normal appearance. What other structures are there that you have to recognize? So here we've already talked about the blue in this picture, blue SVC, right atrium, IVC, and that's how to think about it as a single tube with a swelling in the middle. It's the right atrium. There are several things within the right atrium that you have to recognize. One of them is the opening of the IVC, one's the opening of the SVC, and can you see there's this ridge just round the lip of the IVC like that? That's called the eustachian valve. And that means that blood which flows up the IVC hits the eustachian valve and is pushed over towards the interatrial septum. And you can see the shadow on the interatrial septum of the fossa ovalis, where there'd be a secundum ASD if there was one. And then you can see the tricuspid valve, which leads into the right ventricle. And between the opening of the IVC here and the tricuspid valve here, there's another hole here in the middle, isn't there? And that's the coronary sinus. The coronary sinus drains the blood from the heart muscle itself back into the venous circulation. And if you just look where the coronary sinus is, if you imagine walking up the IVC and walking towards the tricuspid valve, to do that, you'd have to walk past the opening of the coronary sinus, wouldn't you? So that's where the coronary sinus is. That's why because it's so close to the tricuspid valve, that's why pacing wires always end up down the coronary sinus when you don't want them to. You go through the tricuspid valve into the right ventricle. The right ventricle is thin-walled and rough. You know that. There are also multiple pillary muscles, usually at least 3, more pillary muscles in the right ventricle than the left ventricle. And one of the pillary muscles usually arises from the septum. In the left ventricle, pillary muscles never arise from the septum. That's an important difference between the ventricles. Then the blood will go out through the tricuspid pulmonary valve into the main pulmonary artery, which then splits into right and left. And you've got to be able to identify which is which. And goodness, you'll sit in the exam and you'll say, oh, I don't know, I don't know. But if you stop and think about it, you can always figure it out. How are you going to figure it out? Well, what you're going to remember is the aorta is essentially a midline structure. The heart is essentially to the left of the midline, 2/3 of the heart, which is to the left of the midline. So one of the pulmonary arteries goes under the aorta and one doesn't. Which one's going to have to go under the aorta? Well, the left-hand one probably isn't going to go under the aorta because it's already on the left. And the right-hand one has got to cross over to the other side to get to the right lung. So it's probably got to cross the aorta, i.e. go under the aorta. So the one that goes under the aorta is the right pulmonary artery. The other one's a left pulmonary artery. So that's how you can identify them. You can use the same argument, the same idea you can use in echo images as well as these anatomical images. There's this small connection between just the bifurcation of the pulmonary artery and the aorta. That's just that fibrous little thing there. That's the position where ductus arteriosus would exist. Blood goes out the pulmonary arteries, comes back in the goes through the lungs, back in the pulmonary veins into the right ventricle. There's 4 pulmonary veins in the normal heart. Through the mitral valve. The mitral valve is the only bicuspid valve in the normal heart. There are usually two papillary muscles in the left ventricle. They do not arise from neither of them arise from the septum. That's the important difference if you remember. And it goes out through the tricuspid valve into the aorta, which comes up and then loops down. And as it loops round, remember, 3 vessels arise from it because the first vessel, the nominate artery, then splits into the right subclavian and right common carotid. And that's a slightly unnecessary animation that doesn't work anyway anymore. Okay. A tiny bit of embryology, just because there are a couple of common abnormalities that you'll see which relate to problems with embryological development. So if you remember how the fetal circulation works, the oxygen that the fetus does not come from its lungs, it comes from mum's placenta. So in the systemic circulation, the blood gets pumped through the fetal side of mum's placenta picks up oxygen, then goes up the IVC. And as it comes up the IVC, it's already oxygenated, so it doesn't need to go through the fetal lungs. So there are a number of ways that's avoided. One is that as it comes up the IVC, that ridge, which is called a valve, although it's not really a valve, the eustachian valve, points the blood flowing up towards the interatrial septum. As the fetus grows, interatrial septum forms, and it forms by growing from either side, crossing over, and then sticking down to form a wall. That's how the interatrial septum forms, by growing like this, crossing over, and sticking down. In the fetus, it doesn't stick down, it sticks down after birth. So that leaves it a bit like curtains in a theatre. You can push them apart and get through it. And that's the patent foramina valley. So what happens is the blood comes up the IVC, is pushed towards the interatrial septum, which has got this flap in it. It pushes the flap open, and the blood goes into the left atrium. Or most of the blood goes into the left atrium. A little bit still goes through the right through the right ventricle into the pulmonary artery, and then there's another shortcut it can take to stop the blood going into the into the fetal lungs where it doesn't need to go, which is the ductus arteriosus. And that ductus arteriosus is a little vessel which joins the bifurcation of the main pulmonary artery to the aorta. And because the fetal lungs are collapsed, they've got quite high resistance, and the pressure, the blood pressure in the fetal circulation is actually higher in the pulmonary circulation than the systemic circulation. So that blood coming up the pulmonary artery is at higher pressure in the aorta. So most of the blood that's coming up there will then flow through the ductus into the aorta, rather than go to the lungs. Only a small bit goes to the lungs. So that's a high resistance pathway. So that's the fetal circulation. What can go wrong? Well, with the interatrial septum, two things can go wrong. As it grows together, it can stop short like that. And if it stops short, you can see straight from one to another. So it just leaves a hole, which is an atrial septal defect. Or they can cross over and then fail to stick down. So in the adult, you can get this flap persisting because it didn't stick down properly. That's called a patent foramina valley, a PFO, isn't it? And that's really common. About 1 person in 4 has got a patent foramina valley, and isn't really an abnormality. Again, after birth or at the same time as the PFO closes, the ductus should shrivel and close. And if that doesn't happen for whatever reason, the ductus remains an open patent pipe, then the flow will continue, and that's a patent ductus arteriosus. But after birth, the lungs expand and become big sponges, don't they? The resistance for blood to flow through the lungs goes down, and the pressure in the pulmonary circulation goes down, the pressure in the systemic circulation goes up a bit, and the direction of flow reverses. So that if you've got a patent ductus, then in a grown person who's not Eisenmengered, then the direction of flow is the opposite. It's from the aorta to the pulmonary artery. These are two main things that happen in the embryological circulation that cause abnormalities in the adult: PFOs and ASDs and ductus. If you look at the mitral valve here, you can see that there are some strings. These strings are the chordae, and they attach from the mitral valve leaflets to the papillary muscles, which then in turn attached to the myocardium. And if you look where they attach, if this is the mitral valve leaflet that opens and closes like that, most of them attach here around the tips of the mitral valve leaflets, and they're called the primary chordae. But some of them, if you look, join the body of the leaflet, and that they're called the secondary chordae. And a few of them join the base of the leaflet, join the annulus, and they're called the tertiary chordae. So that primary, secondary, tertiary chordae, and their job is to hold the mitral valve leaflet in that position when it's closed, because when the mitral valve leaflet goes to close, all these strings go tight, all these chordae go tight, and it can't come any further back. It's held there by the chordae. So that's the job of the chordae. And if you also look, you can see that both papillary muscles give out chordae to both leaflets. So it's quite a complicated arrangement of chordae. Your picture should be of the aortic valve being stuck right in the middle of the heart. It's the most central structure in the heart. And you're going to need to be able to identify which leaflet of the valves is which. And both in terms of the anatomy and also in terms of the echo. If you think about this, echo image is clearly an echo image of the mitral valve, two leaflets, anterior and posterior leaflets. The anterior leaflet is the one nearest the probe, because the probe's in the front of the chest, so that must be anterior. And then the posterior leaflet is the other one. If I said to you which one's bigger, your answer would be, well, it depends what you mean bigger, sir, because if you mean short, then probably the posterior one's shorter. If you mean length, then the posterior one is longer. If you mean, so think of it like two chaps, like me and my friend Alan, who's coming tomorrow. I'm short and fat, he's tall and thin. Which one of us is bigger? Well, you might say, I mean, which one's taller? I mean, which one's fatter? Or you might say, I mean, which one weighs more? And they both weigh about the same. And this is also true of the mitral valve leaflets. They've both got about the same amount of tissue, because the anterior leaflet is short and fat, the posterior leaflet is long and thin. Both got about the same amount of tissue, so both got equal importance. And then the leaflet is split into thirds. Both leaflets are split into thirds, and they're numbered 1, 2, 3. And that happens because, I've got a paper crumple to show you. Look at that shape there. The anterior leaflet just does this. It opens, lets blood come out, and it closes. Whereas the posterior leaflet, it has to do something else. It's shaped like that, isn't it? So when it's open, it's like this. When it closes, it has to do that to close. And then opens, and then closes. It has to crinkle up to fit into a smaller space, doesn't it? And the way it crinkles is always the same. So you end up with these two indentations in the posterior mitral valve leaflet, because the way it's got to crinkle to close, and those two crinkles happen about 1/3 of the way along and 2/3 of the way along the posterior leaflet, and that's what you use to split the leaflet into thirds. And then the opposite bits in the anterior leaflet are called the same names. So A1, A2, A3, scallops of the mitral valve is what they're called. And you can't see my illustrations. I don't quite know what you mean. I presume you can see the projected slides. Yeah, okay. So there's nothing else apart from, so I'm just talking around the slides. Thanks. So yeah, so the opposite bits of the anterior leaflet are the matching scallops, and this has recently come into the BSc syllabus for transthoracic echo, even though it's something that's much more useful for even though it's something that's much more useful for transesophageal echo. It has come up it's been put in the syllabus and has come up in the exam. So we'll come back to that. This identification of scallops of the valve, mitral valve later. You also got to be able to identify which papillary muscle is which. So posteromedial, anterolateral. If you're struggling to remember which direction is posteromedial and anterolateral on a transthoracic echo, just think of your dad, because it's across the screen. It reads P for posteromedial, then A for anterolateral. It reads Pa, your dad. So you can either figure out the geometry, or you can just remember your dad, which one's which. Similarly with the aortic valve, the leaflet nearest the probe, because the probe is in the front of the chest for this image, isn't it? So the leaflet nearest the probe must be the most anterior leaflet. And in echo speak, we don't say anterior aortic leaflet, we say right, because the word right means things at the front of the chest. So the right aortic leaflet, the right aortic annulus is the one at the front of the chest. The left is never on the left of the screen in either transthoracic or transesophageal echo, and the non-coronary cusp, the non-coronary aortic leaflet is the one near the interatrial septum, which is that one. So you need to remember that somehow. For those of you who are of a certain age, Ronnie loves Nancy will mean something to you. That's one way to remember it. With the four-chamber view, an important thing to notice is that the tricuspid valve is closer to the apex than the mitral valve, and that can be by up to a centimetre, that difference. If the difference is more than a centimetre, then that's abnormal. The heart muscle itself gets its blood supplied through coronary arteries. What happens to the blood once it's gone down the coronary arteries? It goes through the coronary arteries, which split up and split up and split up into the arterioles, supplies the blood, then goes into venules, which join together to form the cardiac veins. And the cardiac veins all join together, as you see here, to join the coronary sinus, which is where the veins, the single entrance of all the coronary veins comes back into the right atrium, which we've seen already. These of these images, it's only the top one that's important. This is the what you see in a suprasternal view, isn't it? So you see the ascending aorta and the descending aorta, and you see the three vessels. If you've got a good image like this, you see the three vessels coming off. The first one, remember, is the big artery, the nominate artery, which then splits into the right subclavian and right common carotid, and then you get individually coming off the arch, the left carotid and the left subclavian, and you've got to be able to identify those arteries. And we've already said already, the pulmonary artery that goes underneath the aorta, which you can see here, is the right pulmonary artery. So we've said most of these things, apart from the last couple. So atrial function, I didn't know where else to put this, so I just put it in here. There are three things that the atrium does, and you need to, you need to be able to describe those, understand those. So this is the left atrium here, and this here is the left ventricle. So during ventricular systole, this valve is shut, and all the left atrium is doing is holding some blood. So it's acting like a reservoir. At the end of ventricular systole, the ventricle relaxes, the pressure drops, and the mitral valve opens. What's happening then is blood is flowing from the atrium into the ventricle, but you know that you don't see that when that happens, the atrium does not collapse away to nothing. So how does it stay full? Why doesn't it empty? And it stays full because at the same time, blood is flowing from the pulmonary vein into the atrium. So blood's flowing from the pulmonary vein into the atrium, and from the atrium into the ventricle. So really, during that phase, all the atrium is doing is joining the pulmonary vein to the ventricle. So all it's doing is joining the two, so it's acting like a conduit. And the last thing the atrium does is it contracts. So you can see the atrium does three things. It acts as a reservoir, it holds blood. then it joins the pulmonary, that's the conduit, it joins the pulmonary vein to the ventricle, and then it contracts. So you know those three things. If I was going to ask a question now in the exam, I would ask a question. I just put this in here just to get you thinking about it. Next time you're scanning, you know, if you remember, what happens is you take your scan head out of the scan. You get a sheet of ultrasound like that, don't you? And wherever you put your scanner, that sheet of ultrasound cuts through in the middle of you. So my question would be about, you know, as you tilt the probe, you know, what things do you see and why? Where is that sheet of ultrasound going as you lift the tail of the probe? This ultrasound is going more towards the head, more towards the feet, and so on. So that, I think, would lend itself, it's not happened yet, but I think would lend itself very nicely to a question to identify people who've done a lot of echo. And then the last thing to mention in this section, because I don't know where else to put it, is about dissection. So dissection is a tear in the wall of the aorta, and transthoracic echo is not a sensitive way to identify it's there. That is to say, if you see it with transthoracic echo, then you've seen it and it's there. If you don't see a dissection with transthoracic echo, it does not mean there's not one. So you can easily not see it because of the way transthoracic echo works. But if you do see it, you need to be able to classify it. And the important classification is the Stanford classification, and that is to say, if the dissection only involves the descending aorta, that's called a type B dissection. And if any involvement of the tear going back past the left subclavian towards the heart, then that's called a type A dissection. And the reason for that distinction is a type A dissection is a surgical emergency and will be treated, you know, immediately by surgery, because the mortality rate in the first 48 hours is extremely high. Whereas type B dissection, which only involves the descending aorta, it's not quite so clear how to treat that. It's certainly not treated by immediate open heart surgery, and you know, it may or may not be the right thing to stent it, for example. So treated very differently. So you need to know the difference between a type A and a type B dissection. And that's all I wanted to say about the anatomy. So any questions you put in the chat box, just while I take a second to open the next talk. So hopefully you can see the next talk, which is about physics. So why on earth are we going to waste our time talking about physics? Well, for two reasons. One is, you might say, you know, you can't fly an airplane unless you know what all the buttons do and how they work. And you wouldn't get an airplane if you saw a pilot who didn't know who didn't know that, what the buttons were and how they worked. And you know, if you're coming for a heart scan, you might say the same thing. I don't want somebody who doesn't know what the buttons are and how they work doing my heart scan. That would be the most acceptable reason. The other reason is a slightly more mathematical reason. You might say, I don't really care. I just want to pass the exam so I can get on with my life. And if that's going to be what you say, then to pass the exam, to pass the multiple choice paper, you need to get something like 75% correct. And if I tell you that 20% of the questions are on physics, which is the case, that means that either you need to know everything else perfectly, and you'll probably get away without understanding the physics. If you know everything else absolutely perfectly, you'll scrape through. Or you need to know the physics. So you can either have a pragmatic or a realist view of why you need to know some physics, but you need to know some physics, I'm afraid. So this won't be so familiar to you. You won't have thought about this since you last did an echo course. So I'm going to go through this a bit more slowly. And then after this and after the calculations, tissue Doppler will start to speed up. Okay. Why this picture? This picture because this is my most favourite place in the world. This is taken from the ridge between Val Thorens and Meribel, looking over at that beautiful picture of Mont Blanc there. And just to remind you, keep concentrating, because you'll be able to go to your favourite place more often if you pass the exam and get a better job. Okay. So I should just say some of the slides we probably won't talk too much about today, because they'll come up tomorrow. But some of these slides are Simon's from GE, and you know, I just like to acknowledge GE. They support our educational program in Stoke really strongly. We run a whole host of echo courses here in Stoke. You know, beginners courses, 4D courses, TOE courses, myocardial mechanics, all sorts of things. And GE have been very, very supportive in terms of sending the people along to help, lending us equipment for the practical element of the courses and so on. So I'm very grateful to GE. What kind of physics do you need to know about? You need to know about the physics of sound, and sound is waves. So you need to know about wave physics. And there are two different kinds of waves. There is the kind of wave you see above, which is in my imagination. That's how I surf, and you see a big water wave, and you can picture that very easily. The other kind of wave is the kind of thing that you might see from Stoke's only famous export. That's not quite true. Or Stoke's most famous export, Robbie Williams, and Robbie makes sound waves. And they're different. And I'm just going to briefly explain to you why they're different, and then why you can think of them in the same way, as long as you remember the difference. So your picture of a wave is something like this, isn't it? If you want to describe that wave, there are a few things that you would describe. What do I mean by describe? I mean be able to, it's a bit like me saying I went to the pub last night and saw this person who was 5'5" and brown hair and blue eyes. It's me telling you the key things about something so you can picture them. So what things do you need to describe this wave? Well, first of all, the wave might look like this, or it might look like this. So it can be short or long. So one thing is the length of the wave, which is the wavelength. The second thing is if you imagine you're standing on the edge of the pier and these waves are going past you, you might say, well, there's one wave going past me a second, or there's 5 waves going past me a second. You might count how many waves go past you a second. And that's called the frequency, number of waves per second. Waves per second is the same as hertz, which is the other unit that's used. And then if you're feeling particularly precocious, you might say, well, if I saw three waves go past you per second, the frequency, and each wave is 2 meters long, then 6 meters of waves, 3 times 2, must have gone past me each second. Therefore, the wave must be moving at 6 meters per second. And that is the wave formula. Speed is frequency times wavelength. And then the last thing you need to describe a wave is, you know, if you walk into the sea on the surfing beach in St. Ives, some days you'll stand in the sea, and other days you'll stand in the sea and boom, you'll get knocked over by a wave, won't you? What's the difference? Small waves will just lap around your ankles and not cause you any problems, but bigger waves are the ones that hit you and knock you over. So the height of the wave is important. How can a wave knock me over? It can knock me over by delivering energy that pushes me backwards. So the height of the wave must be to do with how much energy the wave's carrying. Which reminds me, I didn't actually say what a wave does. What does a wave do? A wave is just a way of moving energy from one place to another. That's all a wave does. And the bigger it is, the more energy it's carrying. So the height of the wave is called the amplitude, frequency, wavelength, velocity. They're the key things about a wave. We talked about water waves. What's the key thing about a water wave? If you watch a lifeboat out at sea, which has switched its engine off to pull somebody out of the sea, the lifeboat does this. It bobs up and down, doesn't it? While the waves do that, they move that way. So in a water wave, the water, the medium is going up and down, and the wave is moving at right angles to it. That's called a transverse wave. Whereas in sound, that's not the case. In sound waves, the medium, the air, is moving in the same direction as the sound is moving. So the air is moving in the same direction as the sound is moving. That doesn't mean that the air molecule that comes out of my mouth ends up in your ear, or worse still, your nose, because you can't tell if we're sitting in the same room if I've got bad breath or not, unless you're very close to me. But what happens is the air molecule vibrates backwards and forwards and knocks onto the next one, vibrates backwards and forwards, and so on. And that knock-on is the transmission of the wave. So that means that's called a longitudinal wave, where the vibration is in the same direction as the wave, unlike a water wave, the vibration is at right angles to the wave. That means you can't picture it like a water wave. So why did I mention a water wave first? Well, actually, if you do this, if you take a sound wave, and you can see here that sometimes the molecules or the wave fronts are close together, and other places they're far apart, and you draw a graph of how far apart the sound waves are, then you see this. That's a graph. The second line down is a graph of how far apart the sound waves are. And actually, that graph looks just like a water wave, doesn't it? So in fact, you can picture a sound wave in exactly the same way as a water wave, use the same things, use the wavelength, frequency, velocity, amplitude to describe it. But you need to remember, it's not a transverse wave. It's not a water wave. It's a sound wave, which is a longitudinal wave. Okay, this bit's really important. This keeps cropping up in exam. If I said to you, think back to old grade physics, what is c? You say, I know, sir, c is the speed of light in a vacuum. It's 3 times 10 to the power of 8 meters per second. That's 300 million meters per second. What's the relevance of that? The relevance of that is, I said to you, I chose a wave, an electromagnetic wave, a light wave. I chose a medium that's moving through, that is a vacuum. And I was able to go away and look up the speed that wave will move in that medium. So it's a fixed number, and I can't change that. The speed of light is fixed. Yeah, and that's true of all waves. So if you choose your wave to be a sound wave, and you choose your medium to be body tissue, then that speed is fixed. That wave will move at 1540 meters per second. If you choose a sound wave and choose the medium to be air, then sound wave and air will move, standard temperature and pressure will move at 330 meters per second, so quite a lot slower, because the molecule, you think of it as being because the molecules are further apart. It's hard for them to knock on. Whereas if they're next to each other, it's easier to have that knock on. And that's really important. And that sounds really basic, but it's a really important fact. Once you've chosen a sound wave and you've chosen the medium, you can't change the speed. If you change the medium, you'll change the speed. But if you stay in the same medium, you can't change the speed. And that crops up commonly in exam, and people commonly get it wrong. What makes a good exam question? Well, if you're wanting 80% of people to pass, if that's the sort of bar you've set, then a good question is one that get 80% of people get correct and 20% of people get wrong. And this is exactly what happens when the questions are asked about this, because people think they understand it and they don't. So really important. If I said to you, what frequency of ultrasound are you using, you'd know the answer. You'd say, I'm using a 3 or a 5 megahertz transducer, something like that. And if you're doing kids, it'd be a higher frequency. If you're using TOE, it'd be a higher frequency. So you know these numbers. And what's megahertz? It means million waves per second. So your ultrasound probe, out of it, produces 2 million waves per second. That's an enormous number of waves, isn't it? So very high frequency. Spoken sound happens at a few hundred or a few thousand waves per second, so much lower frequency. But once you know so you remember the frequency just because you're used to using it, because you're used to saying it when you pick up the probe. It's familiar to you. So you remember the frequency. You need to remember those numbers for the speed. If you know the speed, you know the frequency, then speed is frequency times wavelength, as we said already. Therefore, you can calculate the wavelength. So you don't need to remember the wavelength, just the speed and the frequency. So that's how you describe waves. What can they do? Well, waves can't do that much. They can reflect. And that's easy. Let me just, well, this is there, I don't need to draw it. So for a flat surface, you get a perfect image. And you get, I'm going to draw it. So I'm just going to pull up a whiteboard for a second. Let me share the whiteboard. So if you've got a flat surface and a mountain top here, this bit of light will bounce here. It'll come to the flat surface. The law of reflection says the angle where it meets here to the right angle to the surface will be the same as the angle it bounces off as. So the next polar beam of light will come down here, allowing for my crap drawing, and it'll bounce off there. And you get a very ordered reflection from the ordered beams coming in. So that's why you see that nice picture in the lake of the volcano. However, if a gust of wind comes along, you no longer see that. Why do you no longer see that? If you have a gust of wind, you've now got a lake that looks like that, doesn't it? It's no longer flat. So think what happens. The first beam of light that we talked about comes down there, hits here. There's the normal, the right-angled line. So it goes off there. The next one comes down. And hits here. There's the normal, so it goes off in that direction. So you can see that the effect of a non-flat scattering surface is that you lose the organized reflection, which is why you no longer see the nice picture that you saw before of the volcano. What you see here, with a gust of wind, you no longer see that. So that's reflection. The angle of incidence equals the angle of reflection. You can get scattering. So reflection happened when a wave hit a big surface like a lake or a mirror. So something big, like me walking into a wall, both, I bounce back. Scattering happens when a wave hits something small. So like me, if I'm the wave, not walking into a wall and bouncing back, but walking past a small child and just clipping them in the back of the head as I walk past. Yep, that's that's the kind of process which happens in scattering. The wave hits something small, hits it in the back of the head, it absorbs a bit of energy, it hurts. And what does the kid say? He says, ow. That's just like what happens when a wave hits something small. Wave hits something small, it absorbs a small amount of energy and then releases it in all directions. and that's called scattering. So scattering is a low energy, reflection is high energy, scattering is low energy, because only a small amount of energy is absorbed by the small structure, and then lets off in all directions. And that happens when a wave hits something small. So when does ultrasound waves in the body hit something small? That's when it hits red blood cells. So this is the process that happens when ultrasound hits red blood cells. And when ultrasound hits red blood cells, what process were we talking about? We're talking about Doppler. So Doppler, blood pool Doppler signals come from scattering rather than reflection. Refraction means a change in medium. So, it means a change in direction because of a change in medium. So, let me give you an example. Imagine this 20 years ago, the kids were small and, would go to the sea and a Sark on one side, Fraser on the other side, would run down the beach straight into the water, would run down the beach at high speed, would get into the water, and actually, it's much harder to walk through water, isn't it? So we slow down, don't we? But if we run straight into the water, we all run in, we hit the water at the same time, we slow down together, and we keep going together. Easy. So you run straight in, you go down the right angle to the barrier between the sea and the beach. You go in along the right angle line, you just slow down and keep going. What happens if we run at an angle? So we run down the beach diagonally, what happens? We've got Fraser here, Sorka here. We run down the beach, we get to the water. Fraser hits the water first. So what does he do? He slows down. So he slows down, but me and Sorka are still on the beach, so we don't slow down. So he's going slowly, and me and Sorka are going faster. So we start to turn as we move. And then I end up in the water, so I slow down. So me and Fraser are going slowly, but Sorka's still going faster. So we turn a bit more until we're all in the water together and we keep going at the same speed. So we change direction. That's exactly what you see here in this slide. You see that light beam did exactly that, exactly the way described. It changed direction. As it hit the glass, the left-hand side of the beam hit the glass first, so it slowed down first, whereas the right-hand side kept going faster because it was still in air rather than glass. So it turned round that way, and the opposite happened when it left again. So that's refraction. The important thing is refraction means bending. It happens because of a change in medium. So perhaps going from body tissue to a cyst or something. It happens a change in medium. You can describe it with something called Snell's law, but you don't need to for the purposes of the exam. Diffraction means spreading out. So let me just pull the whiteboard back for a second and ask you a different question on the whiteboard. So here is the harbour wall. Here is out to sea with the waves coming in. Here is a boat in the harbour. You can tell one of my strengths in life is drawing, can't you? So as the waves come in, these ones will completely reflect here and go no further. This bit of the wave will go past the end of the breakwater and keep going down here. My question is, does this boat rock? And the answer is, it might do. Because once a wave goes past the boundary, it starts to stretch out like that. So it might stretch out far enough to reach the boat and make it rock. That's called diffraction, this kind of stretching out of the wave that you see. Really importantly, if this wave has got 5 joules of energy, how much can this wave have as a maximum? It's 5 joules of energy, isn't it? But that 5 joules is spread over a longer distance because the wave is stretched out, then the amplitude will go down. So as this wave moves, it will get a bit longer, but its size will get less. Okay. Diffraction. So a wave can diffract. Transmission we've talked about. You know, I'm too embarrassed to tell you who the band is because nobody will have a clue apart from me. If you they're called transmission vamp or transition vamp, in fact. If you walk, if I was a wafer and I walked into a wall, then some of you would bounce back, or most of you would bounce back. But the guys next door might know I'd done that, mightn't they? Because they might hear something. So some of me, when I come to a boundary, some of them might go on and some of them might be reflected. So a wave will split in general, a wave will split at a boundary. Some will be transmitted, some will be reflected. Attenuation. So this is again quite an important concept. It's quite a hard concept. So, what does a wave do? It carries energy. Imagine that you're on the beach and you are somebody's in trouble at the other end of the beach. So you run into the water. So you're here, they're over there. You run into the water and then walk down through the water to get to them. How are you going to feel by the time you get there? You are going to be knackered, aren't you? Okay, so you would be knackered. But what have you done? All you've done is get to them. You've not rescued them yet. So just moving you from one place to another has made you tired. So it's obviously used a lot of your energy. So just moving from one place to another costs a lot of energy for you walking through the water. Less energy for walking along the sand, but quite a lot of energy for walking through the water. All you've done is moved. So it costs energy to move you. And that's because of the friction of the water and so on. You've got to overcome that, inertia and so on. You've got to overcome those things and they cost energy. The same is true for a wave. If a wave moves from here to here, it's got to overcome friction, inertia, and so on. So that costs energy. So a wave has got to use energy just to move from here to here. And where does the wave get its energy from? Well, the only place it can is the energy that is the wave that it's carrying, you know, because a wave is just energy moving. So if it's going to have to use some of that energy to move from here to here, it's going to have less energy when it gets to here. And how do we know how much energy a wave's got? It's the height of the wave. So as a wave moves from here to here, it's going to have to use some energy. And we can see that because the size of the wave, the amplitude, will get smaller. And that change in size, that loss of energy, is called attenuation. So the further a wave moves, the smaller the wave becomes, the less energy it's got left. So if you've got two identical things here and a wave that starts here, the reflection from the first one has got to go 2 meters. The reflection from the second one has got to go a total of 4 meters. So it's gone much further. So the time the signal gets back after 4 meters, it's going to be much smaller wave that gets back than the one that's only gone 2 meters. So what you would hear if you stood here was you set off a bit of ultrasound, a bit of a wave. You'd hear back a bit, bit. The second one you can barely hear, it's so quiet. And yet, these two things should give you an identical signal because they're identical. So you can see attenuation causes a problem because it makes this one look like a weak reflector and this one look like a strong reflector, even though they're the same. So you need to recognize, so that's what attenuation is. That's the problem it causes. So you need to recognize that by when you are listening, the further away the signals come from, the more you need to turn up the volume. so you can hear them the same. So you hear bit, bit, rather than bit, bit. So that means you need a different volume at different depths. Volume, of course, is just gain. So you need to change gain by depth. So because of attenuation, you need different gains at different depths. And one of the ways you achieve that is using the time gain compensation on that set of sliders on your echo machine, isn't it? Okay. So that's all the things that waves do. How do you make them? Well, you make waves by using a transducer. Now, if you go to an X-ray department, they'll have a fine selection of transducers like this. Of course, you know in the echo department, you've only got the middle one. The reason you can't, you'd like to have the curved one. If you had a curved one like that, it would shoot out beams in all directions and cover the whole of the heart. Why? And if you go and have your belly scanned in an X-ray department, that's what they'll use. Why don't you use that for the heart? You don't use that for the heart just because of the very first slide we saw. There's only small gaps around the place where you can put the probe that it doesn't come across lung. So the probe needs to have a small head. So you can't use the sort of standard array probes. You've got to use a phased array probe, and we'll come back to exactly what that means in a moment. And the reasons you've got to use a phased array probe is because it is, in fact, we'll come back to that tomorrow, not later. What a phased array probe and how it works is because it's got a small head. In the head of the probe, whatever kind of probe it is a series of crystals. And it's the crystals that make the ultrasound. How should you think of the crystals? You should think of them like a gong. So that's a picture that should be in your mind. Because if you hit a gong, it makes a note. If you hit a gong, it goes dong. If you hit a gong again, but harder, same gong, but harder, it goes dong. It makes the same noise, but louder. And you can't make it make a different noise. If you got a different noise from it, you need to have a different gong that's got a different shape and thickness, don't you? Which is why, you get all these, marching bands of all different triangles of different sizes and stuff like that. The sound is determined by the size and shape of the gong. The volume is determined by how hard you hit it. So ultrasound is made by crystals with that special property called the piezoelectric property. The piezoelectric property means that if you apply a voltage, and what's a voltage? A voltage is, if you think a simple circuit with a battery and a light bulb, the number of electrons flowing around it is the current, the resistance is how hard it is for the electrons to move, and the voltage is the push, the electrical pressure, the push that the battery pushes the electrons round with. So if you apply that electrical pressure, that voltage, to a piezoelectric crystal, so connect up a piezoelectric crystal to the battery, and what happens, the piezoelectric effect is that the crystal changes shape and size. And then you switch it off and it relaxes back. You switch it on, it changes shape and size. Switch it off, it relaxes back. So that's the piezoelectric effect. The piezoelectric effect is just that. If you change the voltage applied, the crystal changes shape. If you change the shape, it creates a voltage. That's the piezoelectric effect. And in fact, if what you do to a crystal is you switch the voltage on and off quickly, it changes shape and back again quickly. That's a bit like a gong being hit with a hammer, and it starts to vibrate and makes an ultrasound wave. And the frequency of the ultrasound wave is determined by the size and shape of the crystal. So what you do is you choose the size and shape of the crystal to give you the frequency that you want, and then you hit it to set it vibrating by switching on and off a voltage quickly. That's how the crystals in the probe create ultrasound. Once you've made a beam, this is easier to demonstrate in that if we're all in the same room. if I unfocus the projector that we're using in the same room, then you can't read this anymore. You can't read it because all of the lines stop being narrow. So the black lines or the black writing stops being narrow and becomes wider and much more blurred. So to see a sharp, focused image, you need to have a narrow beam, and that's what this shows you. And that's what focusing is. It's keeping the beam narrow, and you can only focus within what's called the near field of a beam. And the length of the near field is determined by the transducer head size and shape and the frequency. And that's fixed. And you can only make the beam narrow within the near field. And once you get outside the near field, whatever you try and do, the beam gets wider. It spreads out. A bit like diffraction. So the narrowest point of the beam happens at the focal depth. The focal depth has to be within the near field. You just need to know those words, and we'll talk tomorrow in some of the questions about how you focus a beam, how you focus a beam from a phased array probe. Okay. So the next question I would ask if we're all in the same room is, who uses second harmonic imaging? And usually the response to this is everybody looks at everybody else, and then one or two people says, I do. And the answer is, you all do, because all contemporary echo machines work on second harmonic imaging by default. You can switch it off, but you have to switch it off now rather than switch it on. And it's marked in different ways. You know, nowadays we only use GE machines and Stokes. So I've lost familiarity with the other brands, but in GE, for example, it will say on the screen 2.3 stroke 4.6, and that's telling you it's second harmonic imaging. Because what those numbers mean, 2.3 stroke 4.6, is you're transmitting at 2.3 megahertz, but you're listening at 4.6 megahertz. Doesn't make much sense, does it? So the maths is too complex to try and explain and doesn't matter. I'm going to tell you what I think today, and between today and a couple of questions tomorrow, I'm going to tell you what I think is important to know about second harmonic imaging. It has cropped up in a question before, which is why I've made a bit of an effort to make sure it's included on both days. So imagine a newborn baby, pure as a driven snow. Yep. And then look at my kids who are in their mid-20s now, no longer pure as a driven snow, and have become a bit corrupted as they've got older. And what's happened? They started off as perfect, innocent, pure babies, and they had interactions with things as they grew up. Interactions with us as parents, and interactions with their friends, interactions with people at school, teachers, slightly more dubious characters along the way, I'm quite sure. You know, the university would meet some really dubious characters, and as they met all these people, they interacted with them both ways. That changed them a little bit, and gradually they built their own personality, which is a really corrupt. I don't mean they're corrupt. I mean what their personality is a mixture of all those things that they've interacted with as they got older. So no longer pure. Something very similar happens to an ultrasound wave as it propagates through anything, through any medium. So it starts off as a pure 2.3 megahertz beam, but immediately it bumps into stuff. It bumps into muscle fibers, it bumps into blood vessels, it bumps into fibrous tissue, it bumps into all sorts of things. Each time it bumps into those things, it will scatter or reflect off them, and then that reflected beam will come back and interact with the main beam and change the main beam a little bit. so that in the same way as the kids change as they go through life, the beam changes as it goes through a medium because it interacts with the medium around it. And mathematically, you can describe that as beam stops being just 2.3 megahertz, but becomes a beam that's 2.3 megahertz with a bit of twice that, so 4.6, with a bit of 3 times that, 6.9 megahertz, and so on. And you can describe that mathematically. So that you stop just being a pure 2.3 and you get some 4.6 and 6.9 and so on and so on and so on. And the further the beam moves, the more that mixture happens. So that if you're looking deep into a structure, you'll see the deeper you're interested in looking, you'll see more and more of the 4.6 megahertz coming back rather than the 2.3. And that's second harmonic imaging. So you transmit at one frequency, you listen at twice the frequency, you get a mixed signal back because of that interaction. You see things that are deeper, further away, better, and things that are in the middle of the beam better. You'd quite a powerful beam to do that. So you need a high power beam, and it changes how things appear when you use second harmonic imaging. Everything looks a bit thicker and a bit coarser textured. And then the last thing is you need to know about compression, dynamic range, and reject, and we'll cover those in a question tomorrow. Good. So that's roughly what waves do, how you make them. How do you make images? So you know this, you make 1D images, which are M mode, 2D images, which are grayscale images, and 3D images. They all work on the principle that this £100,000 you have just spent on your new Echo machine, £100,000, you've just bought yourself a stopwatch. That's a principle this whole thing works on. So essentially what you do is you send out a bit of ultrasound. So you send out not a long wave, but just a bit of ultrasound. So a short wave like that. So a wave packet is called. You have a bit of ultrasound that goes down the scan line, and every time it comes across something, some of it's reflected and some of it's transmitted. So you send off a bit of ultrasound, and you get back bip, 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 3 bips. And what the machine does is it times how long it takes for between the bip leaving the scanner and the bip coming back to the scanner. So it might say the first one took 2 seconds, the second one took 3 seconds, and the third one took 4.5 seconds to get back. If you know that you're moving at 3 meters per second, yep, it took 2 seconds to get the first reflection back, then it must have moved 3 meters per second for 2 seconds. It must have moved 6 meters, because distance is speed times time. So 6 meters there and back. So the reflection must have happened 3 meters away. So you can put a cross 3 meters away and say there's a reflecting surface there. And that's how the Echo machine works. It times how long it takes for the signal to come back, and then you use distance equals speed times time. And you know the speed because it's 1540 meters per second through average body tissue. So, for example, here, this first image is taken down through it's an M mode through the mitral valve. You get a reflection, first of all, on the right ventricular free wall, bip, then 2 reflections on the anteroseptum, bip, bip, then 2 reflections in the mitral valve tips, which are together, bip, and then 2 reflections from the posterior wall, bip, bip. If you repeat that a moment later, then the only thing that's happened is the mitral valve leaflets have started to move apart. Repeat again a moment later, the mitral valve leaflets have moved further apart. What the machine does is it then joins them, interpolates them, it's called, joins them together side to side to make straight lines, and you get M mode. M mode on the left-hand side of the screen of the aortic valve, and on the right-hand side of the screen of the mitral valve. How do you make a 2D image? Well, it's essentially the same thing. Sorry, and M mode, if you're only going up and down one line, Typically with echo, that means you go up and down that line 1,000 times a second. So really quite high frequency. How do you make 2D images? Well, you just work your way around, taking a line at a time. So you take a picture down this line, send a beam, get it back, bip, 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 mark where the things are, down the next line, bip, bip, and work your way around the sector, doing that one at a time until you've got a picture of where everything is within that sector. And you might take 40 lines. So then you go back and do it again. And then you go back and do it again. And then you go back and do it again. What you see is you see how things change with time. And of course, if you're taking, instead of taking, if you do one line 1,000 times a second, if you've got to take 40 lines to make your frame, then you can only do that. You can only make 25 frames in a second, because you can still only take 1,000 lines in a second, can't you? So 25 times 40 is 1,000. So although you can do 1,000, a frame rate of 1,000 for M mode, your frame rate for grayscale imaging might be 25, because you've got to take so many lines. So to make the movie, you take one grayscale image, then the next grayscale image, then the next grayscale image, and you just run them together to make a movie, much like what the butler saw in the old-fashioned things used to get in the pier. Okay. Resolution we'll talk about tomorrow. Resolution is just how close together you can tell things apart. So if you know there's one thing or two, and that can either be in space or in time. And there's a couple of questions on that tomorrow, so I won't get too bogged down in that today, except to say that for I'll just pull up the whiteboard again for a second. So if you were to tell two things apart here and here, side to side, essentially what you need to be able to do is this beam comes down and bounces back. This beam goes through, and this beam comes down and bounces back. So you get, this beam gives you a bip, this beam gives you nothing, and this beam gives you a bip. So if that was the case, then you would know that there's two things here, one here, and a gap in the middle here, because that beam went through. If these beams were this wide, that would work. If these beams were this wide, then that wouldn't work, because this is too wide to fit in the gap there. So some of it would always reflect back. So lateral resolution, the ability to tell things apart side to side, is determined by beam width. And when you think about taking so that's the first thing. Lateral resolution is determined by beam width. When you think about taking your your usual shaped picture of an echo like that, then if you've got 40 beams here, what must happen to that beam as the sector gets wider? The beam gets wider, doesn't it? Like that. Each single beam gets wider because it's got to cover, 40's got to cover a wider distance here than it has to carry here. So that means that the beam width depends on depth. So the beams are attributed to a wider distance the deeper they are in the image. So that means, because beam width determines lateral resolution, that means you've got good lateral resolution at the top of the screen and less good lateral resolution at the bottom of the screen. I'll come back to that tomorrow. So look, it's 10:40. I've got there's 10 minutes talking about Doppler physics. Afterwards, then we'll stop talking about physics, and we'll move on to other things. But we'll do lots more physics tomorrow. I suggest we stop now for a break until 5 to 11. We'll come back at 5 to 11. So go and have some coffee, come back at 5 to 11, and we can carry on then. And if you've got any questions, put them in the chat box and I'll deal with them. So stop now for a 15-minute break till 5 to 11, and then we'll finish off the physics after that.